Well, is everyone having a good time? Any good shows so far today? Any good talks? Some good ones? So I can strive for a low level here? Okay, just want to make sure. This is Hydrogeology 101. So if you're here for the pumps, I think that's next door. We'll wait for a few more people to get seated here and we'll get started. And I'll give the code for the CEU credits after we're done here. If I give it to you now, everyone gets up and leaves. Yeah. You can come on in and have a seat. It's okay. Oh, nice. Get all the students up here in the front. That's good. Set an example. They're short, so I'll let them sit there. Especially Nancy here, she's like 4'1". Okay, we'll go and get started here. I'm Dr. Richard Laton. I'm an associate professor of hydrogeology at California State University-Fullerton. For those of you who are not from the California area, that's Cal State Disneyland. We are about 3 to 4 miles away from Disneyland. What makes Cal State Fullerton even more connected to Disneyland is they both opened in the same year. And our campus is a really ugly campus. Apologize, sorry students, but it's a really ugly-ass campus. And it's big boxes. And so the rumor has it that when Disneyland came in, they unpacked it. We got the boxes. And since the state of California is broke, it makes a lot of sense because they've never been wealthy. So anyway, we're going to talk about Hydrogeology 101 today, and I'm going to take you kind of through the water cycle. I'm even going to give you a little math. It's okay. And to give you a little history about me and how I got into this business, I have an oceanography degree from St. Cloud State, Minnesota. Now, if you know where Minnesota is at, and St. Cloud is in the middle of that country, so it's almost its own country, you cannot get further from an ocean than St. Cloud, Minnesota. So when I went to apply for graduate school, nobody would take me. Okay? And my GPA might have sucked, so that's okay. But somehow I found a group at Michigan, at Western Michigan University, that took me in because I had some pretty good math skills. But what was more interesting, why you guys should pay attention here, is they had a drilling rig. And they learned that I drove fork truck one summer for 3M. I was an intern at 3M and whatnot, and so I drove fork truck. And so I went out with them one day when they were drilling some environmental monitoring wells for a thesis, and I lifted the sands of cement around and the sand and grout and everything. And by the end of the day, the head professor walks up to me and goes, "Hey, I heard you drove fork truck. You're our driller for the next 7 years." Okay? So, in my graduate career, I put in nearly 1,000 wells, as deep as 200 to 300 feet, most of them shallow. But I was their driller. Now, how did I learn to do that? From a fork truck driving skill set? I went out and talked to every contractor I could find and asked them, teach me. Okay? So I actually got my hands dirty. So when I got my doctorate, I actually was in the drilling business. Okay? So I've actually done a lot of that. So I'm going to try to put into hydrogeology here the context for which it makes sense to everybody. Okay? So the objective today is just get a better understanding of groundwater and groundwater principles. Like I said, we'll throw in a little bit of math in there, nothing too serious, but I have to do that. I'm a professor. And we're going to go through some different things associated with it. So hopefully today you're going to get some basic definitions so we all have the same verbiage to deal with. We're going to talk about the hydrologic cycle because groundwater is part of it, despite the fact our elementary schools don't teach that, okay? Which really pisses me off that in the K through 12, groundwater is a forgotten subject. And yet it's what we usually get most of our drinking water from. But we'll talk about aquifers and clear up some mysteries about confined aquifers and semi-confined aquifers. We'll talk about some water budgets, some wells and contamination, and then also show you some of the tools that we do to investigate things. So some definitions, just so we're all on the same page. We're the only planet with liquid water. Okay? Pretty important. The hydrologic cycle. Okay, what is it? Okay, we get evaporation. We get condensation, we get precipitation, and once it hits the ground, it can either run off or it can infiltrate in. The stuff that infiltrates in is what's important to us, right? Because that's what groundwater ends up being. Now, where along that cycle happens, a lot of different things can take place. Okay? And where precipitation happens and weather, and we're going to talk about some of the weather issues associated with it. Hydrology. Why would we care about hydrology? And hydrology to me is the study of surface water. Hydrogeology is that water that resides in the dirt. Okay? But hydrology is connected to that dirt for which the groundwater is connected. So there's a connection there, and we got to talk about that. Because that's certainly something that's a hot issue in a lot of states. How can I pump over here and not impact this? Okay? And I'm going to tell you some stories about how Orange County, California, deals with it. Unsaturated zone. That's that zone of air and water that resides above the aquifer. Okay? So there's some water in there, but primarily it's not 100% saturated. And we're going to show you some slides, and we'll talk about that a little bit further. The water table will define it. We'll define an unconfined aquifer and a confined aquifer, and then I'll have to throw Darcy's law in there, and we'll talk about a couple other things. So, distribution of water on Earth. Okay. Most of the water, as everyone knows, resides in the oceans. Okay. Is it potable? No. So most of the water on Earth is not drinkable as is. Okay. So that narrows our little piece of the pie that we're all interested in to pretty small. Okay. So fresh water is about 3% of the total water on Earth. Groundwater makes up a large portion of that. And I like this little slide here because right there is all the fresh water on Earth compared to the volume of Earth. Okay. Groundwater, you can't see it, but there's a little tiny dot down here in one county in Arkansas. Okay. And that's really the potable water source we have for the whole world. Okay. So it's pretty small. So it's something precious to us. Now, it doesn't mean we can't take that salt water and desalinate it and do some other things to it. And people are doing that. They have to. Can't keep raising the population and keep your pie the same size and force everyone to live. So, what is the hydrologic cycle? There again, we have open surface waters where water evaporates. We have plants that transpire and sweat just like we do. Every time you sweat, you're taking liquid and you're turning into a gas phase. Smell a little bit, but it's okay. That goes up in the atmosphere. Okay? Water evaporates as pure H2O. Okay? So when it evaporates, if there's any contaminants in it, be it salt or any kind of pollutant, that's left behind. So when water evaporates, it only evaporates as pure H2O. That's why we distill water. Okay? Once it gets to the air, it cools down and condenses, and at some point in time, the weather system floats over, it condenses, and it precipitates out. Now, precipitate out as snow, rain, sleet, whatever. Doesn't really matter to us. At that point in time, we can have infiltration going into the ground and moving through as groundwater, or we can have runoff. And certainly runoff has some opportunities for groundwater recharge, but we're not going to talk about that. One of the things I want to bring up, though, which I think is going to be a bigger player as we move forward, is what I call the urban water cycle. Okay? The county that I live in has 4 million people. We recycle 100 million gallons of wastewater every single day back into our drinking water supply. Okay? 100 million gallons of water that we treat and put back into the ground. All of the drinking water we have in our county is groundwater. We pull it out with pumps and wells, but it's all recycled water. We're 100% sustainable in a desert. What's going to happen is we're going to start seeing people start using their water for whatever purpose, having that go back in the ground, and then we're going to pull it back out as some kind of usable. Now, we have to treat it. That's going to happen more and more. One of the issues that came up was someone was talking about Minnesota. Anybody here from Minnesota? Good, we can make fun of them. Okay? Hey, it's Minnesota. You got to make fun of them. Okay? They're land of 10,000 lakes. What's their problem? They're running out of groundwater. It's the land of 10,000 lakes. How can you run out of groundwater? Every one of those lakes is tied to the groundwater system. How can you be running out of groundwater? What's their water cycle? They pump it up, they use it, they put it in the Mississippi River and give it to Iowa. Anybody from Iowa? I can make a lot of fun of the Midwest. This works out well. Okay? So they just give their water to Iowa. Well, they already paid to pump it. They already used it, paid to treat it, and then give it to Iowa. Why in the hell would you do that? Just put it back in the ground in Minnesota and keep it. And that's something they're going to have to look at. Okay? So we're going to take, rather than letting that water all go down the rivers to the ocean, we're going to actually start short-circuiting that system because it's something we're going to have to do. It's more sustainable. We're already paying to treat that wastewater. Why not reuse it again? Okay? And you can do this on a private property with a single well as well as everything else. Because what we've been doing, right? You have your septic tank, goes to the leach field. Where do you think that water's going? Right back to your well. You pull it back out. Now, it's been filtered and cleaned by the time it gets back there, but it's the same water. You know, it's like my 8-year-old daughter. She went up to some friends. We were on vacation last week, and she goes, you know, that water you're drinking was dinosaur pee. You know, all water on Earth is recycled. You know. And just here's another nice little picture I like from the USGS talking about the water cycle. It gives us a few other terms in there. Nothing we're too worried about. Certainly there's storage, but groundwater is the one we're worried about. And there again, you know, when you pull it out and use it and put it back in, you're just keeping the system going. Why give it to the ocean? So meteorology, why would I talk about that? Well, remember in the water cycle, it's the first step, right? So we have to talk about climate. Okay? Lots of things out there with climate change, global warming, all these things. Okay? Is it true or not? Okay? I know my audience. Okay? I'm not going to sit here and say global warming. Okay? Climate's changed, though. 12,000 years ago, Chicago had a 1 mile thick sheet of ice on top of it. Okay? Mile thick. Is it there today? Anybody been to Chicago lately? January, it feels like it, but it's still not a mile thick. Okay? That was 12,500 years ago. Were there a lot of cars driving around? Coal-fired power plants? No. Climates change. They warm up. Now, what the impact of human impact is on that, I don't know. There again, educate yourself and get your own opinion. But it does change. Okay? And so it's going to change. It has changed in the past and will change in the future. Temperatures impact groundwater resources. Notice this big yellow area is in the west, and we don't have a whole hell of a lot of water. Lots of water over here. Okay? Other factors is location and altitude and latitude. But all of that precipitation dictates what kind of groundwater resources we have. If you don't have a lot of precipitation, you don't have a lot of recharge, and therefore you're limited in your groundwater supply. The other thing that's important, and I bring this up mainly because of the West Coast, it's not so important for you guys, is the rain shadow effect. As I tell my students, is Pacific Ocean, largest water body on Earth, lots of evaporation. What direction do the weather systems usually go in the United States? From west to east. What happens, that evaporation goes up, the condensation happens, but that cloud is really heavy. It's got a lot of water in it. So it hits that first bump, which in our case is the San Bernardino or San Gabriel, but it would be the Cascades or the Rockies. And what happens is that cloud can't get over the hill. So it precipitates out, rains, snows, lightens its load till it gets high enough that it can float over. So we end up with this area on the backside which gets less rain. So you end up with a desert-type environment. The Mojave Desert would be a great example. Okay? But also, Nebraska and the Midwest, through the Rockies, have a rain shadow effect. So on the one side, they get lots of rainfall, very little on the other side. So surface water. There again, we can talk about it in all kinds of different fashions, from swamps to rivers to oceans, aqueducts like we have in California, nice pretty lakes, but nonetheless, it's a way for the water to move over. Now, it's always touching the ground. So it can be a gaining stream or a losing stream. What do I mean by that? Certain locations along that water pathway, the water is actually going into the ground. It's losing. You know, 100 gallons come in, it's only 50 go out. Where do the other 50 go? Into the ground. Other places, that water's coming in. It's a gaining stream. How do you know the difference? By looking at them. Does that stream flow year-round? Why is there water in that river and it hasn't rained in months? That's because groundwater is discharging into that creek or stream, allowing it to keep flowing. Okay? Where if you go to the Mojave River, it's a river with no water. Because when it does rain, water goes along it for a ways, but it's always going to the ground because the groundwater is about 900 feet below it. Okay? So in the Midwest, you don't have to worry about that so much, but us West Coast people do. And the way we study surface water is we look at what's called a hydrograph, which is really time versus discharge. So here, maybe a rainstorm happened and we get a little bit more water in the river and down, it gets dry for a while. And so you can kind of look at things over time. And what happens is, water's going down and we get this big peak because the rainfall happened. Then over time it dissipates. Well, if you can imagine when water hits certain parts of the watershed, it takes a while for it to get to the river. And so that tail gets drawn out. Now, from planners and engineers, they're always trying to figure out how to take this peak and knock it down, because that peak is what causes mass flooding. Okay? In certain areas, that's why we have flat rooftops on big buildings. They actually want to store some of the water up there so it doesn't hit all the storm sewers or storm drains at the same time. Because if all that water went to the storm drain, you can't make a big enough pipe for that flow. So in order to do that, they store the water temporarily and then try to discharge it over time to those surface water bodies. And so here's a nice illustration showing a gaining stream. There again, groundwater is feeding that surface water body. This could be a lake or a stream or a river. It doesn't have to be just a stream. But groundwater is actually coming into it and discharging and then flowing over. And other times where the river is actually higher or the lake's higher than the groundwater and you see it going out. What's interesting, what I never thought of was, this is great, this is book stuff, right? But the Mississippi River has places along it where it's gaining and places where it's losing. So it doesn't always have to be the same for every inch of it. In fact, one of the things I did for my dissertation was look at the Kalamazoo River in Michigan. There, over a stretch of 50 feet, it switched to 100%, whereas 100% gaining to 100% losing over a 100-foot stretch. And it did that at different levels down the thing. So it can be really short-lived, but nonetheless, it's that interaction between that surface water body and the groundwater, which we're really talking about. So let's talk about groundwater. Okay? That's the water that's in the soils or in the rock. Okay? It's the stuff that sits in between all these fractures and these grains. Okay? It's stuff that we can't see. What I love about groundwater and love about teaching about it is you can't see it. So I'm always right. You can't prove me wrong. Surface water, any monkey can teach that stuff because you can go out and touch it. You can't touch groundwater unless you do something with it. That's either go to a spring or put a well in the ground. Okay? And so, what is it? It's the water contained in spaces within soil and bedrock. It's less than only 1% of all water on Earth. But it's 40 times more abundant than lakes and streams. That's the key. The groundwater, even though it's minimal, it's still so much bigger than all that fresh water that everyone thinks the surface is great. And our politicians can vote on big river projects because they can see it. Tough to vote on a big groundwater project when you can't see it. So, some other terms. Zone of aeration or vadose zone or unsaturated zone. That's this zone from what we walk on down to some level which I'm going to call the water table. At that point, everything is 100% saturated with water. So all the void spaces in between the fractures and the sand grains or clay or whatever else, it has water in it. Above that water table point is what the vadose zone is. And in here we can have water, but we also have air. It's not 100% saturated. And it has to have some water because the water had to get from here down. Okay? So those are some terms. So we have this as the vadose zone or unsaturated zone. Down here we have my aquifer, and that's the saturated zone because everything is filled with 100% with water. And the water table is the boundary between them. Now what makes it complex is this is what's called an unconfined aquifer. So if I was to just dig a well, there's no clay in there, there's just sand, go down my sandbox, I hit the water table, it's pretty easy to recognize. Okay? It's also, for those of you who dig in sand and gravels, it's right where the hole starts collapsing on you, right? Because from there, that point on, the pressure is into my hole, not out of it. Above it, I can keep the hole open just by digging a hole. So, what is an aquifer? Well, this is a definition, not necessarily the best one, but it's a body of rock that's sufficiently water permeable to yield economical significant quantities of water to wells. Okay, what the hell is economical? I have no idea, because in everybody's book it's going to be different. Okay? To me, the aquifer is that first body of water, or first soil unit that's 100% saturated with water, regardless if it's rock or whatnot. The key is going to be this unconfined and confined. Now, you've got karst around here, so it's probably an unconfined aquifer for the most part. Is that right around here? I mean, does it go up and down with barometric pressure changes? When it rains, do you see a response in your wells in Tennessee? I don't know. Anybody here from Tennessee? At least one person brave enough to raise his hand? That's good. An unconfined or confined. Unconfined to me means that when water hits the land surface, it can go unimpeded down to some depth at that water table. There's nothing to slow it down. It goes straight there. It also means when you have a weather system come through and the barometric pressure changes, I can actually see the water level go up and down based upon that pressure system. A confined aquifer is just that. It has some rock or clay unit that is semi-permeable or impermeable sitting on top of it, allowing pressure to build up below that. And so when it rains, the water doesn't get there directly. It has to go somewhere else, maybe recharge from a distance away. Okay? And so I'm going to show you a picture here, and hopefully we can talk about that a little more. Well, here's another one. You guys don't have a lot of faults around here, do you? Okay, anybody from Tennessee? Is there any faults around here? Okay, then there are some faults. But they can be a conduit for flow or a barrier to flow, and depending on what they are. And this is some research we've been doing is some of the rock units, we're finding these are actually, the faults are actually acting as rivers, underground rivers, as much as I hate that term. But here's a picture of Orange County's aquifer. Each of these blue or brown things represent confining units that are pressurizing or allowing the water down to be pressurized. We have recharge up here that feeds this middle of this basin. We'll talk a little more about that in a second. So confined aquifer, as we see here, has a confining unit on it. Has a rock unit that's not allowing water to perfectly move through it. Now, one of the questions, or one of the things I always tell my students is, everything is permeable. Given enough time, water will find its way into anything and everything. That time is the question. So when we think about confining units, we're looking at something that takes hundreds of thousands of years to get through it. Okay, it'll get through it. You put water on this table, sooner or later it will get through it. Okay? But how long will that take? You can actually have some perch systems as well here, where you have what's called an aquiclude or an aquitard, just different schematics for the same thing. But you can have water perched on top of it, even though you have some beta zone down below it. So that's something that happens in the glacial areas quite a bit. I mean, we're finding all kinds of little thin silt units that were holding 5 or 6 feet of water. You drill through that, it's dry. Okay? And for contaminant work, that was really horrible because you drill through that little 1-inch layer pretty quickly. And all of a sudden cross-contaminate something that wasn't contaminated before. So here's my little scheme. Bunch of wells. Here's my vadose zone. So in here I have both water and air. But then I have my water table. Okay, so this is an unconfined aquifer. It goes up and down with rainfall and barometric pressure changes. However, here I have a rock unit or a barrier to water moving across it. And down here I have another aquifer. Now, where did this water come from? Probably from something off to the hills somewhere. Okay? But it's under pressure. So how do I get an artesian well? Well, when I drill into this thing, if that water level comes above the surface, we call it artesian. But where did that pressure come from? That elevation for which the water will rise here is equal to whatever the recharge elevation was at some distance away. Okay, does that make sense? Okay, so up in the hills, that's why you can get water flowing nicely. These are the kind of wells everyone likes to do. One of the things I want to point out here is that the water in this well, which is screened down here, is higher than the water in this unconfined aquifer, then the pressure is upward. Okay? Water moves from high pressure to low pressure. So this means that this aquifer is pretty well protected because its pressure is out of it, not into it. Where this one, since the water level is lower in this one than this one, the vertical gradient is downward, so this could be a potential aquifer for contamination transfer. Okay? So that's one reason why, if you're ever doing environmental work, we put in nested wells. What I mean by nested wells, 2 wells next to each other, but screened at different depths. We want to know if the water is moving downward or upward. Okay. Some other big words that we use in hydrogeology: homogeneous and heterogeneous. Homogeneous means it's all the same in all locations. So beach sand is nice that for properties of geology. Heterogeneous is going to be the clay, or glacial outwash that has all kinds of stuff in it. And then there's isotropic and anisotropic that we can talk about later. So what's that mean for, when I was drilling? It meant porosity and permeability. And what's the difference? Okay, porosity is that number we give to the volume of water a soil can hold. Permeability is, can that water move through that soil? So one of the things I always tell my students is, what's the porosity of sand versus porosity of clay? They're about the same. They hold about the same amount of water. Somewhere around 35 to 45% they can hold water. But permeability, which is what I really care about, is how that water moves through it. Clay is pretty low. Sand, pretty good. Okay? So we get confused a lot of times by talking about the porosity of stuff because it may be the same porosity value, but the permeability is what I really care about because I need to get that water to my well. And I want to know how it's moving through that aquifer. So permeability is probably a better verbiage to use when we're trying to deal with water issues. Which brings me up to well sorted versus poorly sorted, or well graded versus poorly graded. Now, was a McElhaney lecturer in 2009, so I don't know if any of you guys heard me give my lecture on soil classification. Hopefully you did, and actually hopefully everyone is out there doing the unified soil classification system for the rocks and soils, right? No one has a clue what I'm talking about, right? That's good. That's glad I spent 56 weeks of my life traveling the goddamn country and no one paid attention to me. Well, it's like the thousands of students I have that never listen to me either. Anyway, grading and sorting. We can relate this back to permeability. It goes to grain size. Okay? What I like to start with is grading. Okay? Grading means that when I grade my class, I have a bunch of students get A's, some get B's, C's, D's, and F's. A well-graded class, according to the university, is I have equal numbers of grades for each of those categories. Poorly graded would be I give my whole class a bunch of C's. Okay? So when we relate that to rocks, poorly graded means I have all one grain size. Well graded means I have some clay, silt, sand, gravel, and boulders. Sorting is opposite of grading. So if something is well graded, by definition it's poorly sorted. If it's poorly graded, it's well sorted. So just think of them as flip-flopping them. So in this case, what is this one? It's well sorted, so immediately it would be poorly graded. This one's poorly sorted, so it's well graded. And you can see it has a little bit of every different size. This one's all pretty uniform. What's important about that is from a water production standpoint or groundwater, right? Which one is water going to move through easily? This one or this one? It's going to do this one, right? Because everything's about the same. It's like putting a bunch of marbles together. If I add BBs to my marble collection, it plugs up all those places for that water to go through. So it makes it more difficult. So from a permeability standpoint, this has a much higher permeability than this guy does. So just because you find some gravel in there, that may be great, but if there's a lot of clays and silts tied with it, that can be plugging up your aquifer. And the same thing can be happening with fractures, okay, and karst systems. It's great that I have all kinds of large cracks down there. But if they're not connected to another crack that ultimately connects to your well, what good does it mean? It's great for storing water because the porosity is high, but the permeability is low because there's no connectivity between cracks and fractures. So it's that permeability or that connection between all those that's really important to us from a groundwater standpoint. What am I doing in time? Plenty of time. We'll skip this one. Some of the ways we look at this, and another term you're going to hear a lot, is hydraulic conductivity. Hydraulic conductivity, think of that as permeability. It's the rate for which water can move through the rock media. And we have some different ways we can test that. We can sieve them. We have these little fancy permeameters that you only see in colleges. No one in his right mind would ever do it outside that. But this kind of gives us some idea of, there again, shales are pretty low, karst limestone is pretty high. It can be up to several hundred feet per day. Down in Texas, they did a study and they did some dyes and they dropped them in one part of the aquifer, shot out about 1.5 miles within 2 days. That's moving pretty quick, So, depending on what you're in, it can change that permeability / hydraulic conductivity. But for the most part, groundwater moves pretty slow. Okay? It's not really a fast-moving system. Why? Because it's on a tilt, and I'm going to show you that here in a second. It goes from high pressure to low pressure, and it has a bunch of rocks it's got to get through. So it's like you trying to get through a crowd at the airport. The bigger the crowd, the harder it is for you to get through it. There's no one there, you fly right through. Which, by the way, how many people flew here today, this time? Did you have to go through the whole security thing? Because they pulled me aside, which I thought, oh shit, now I'm going to be strip searched for whatever reason, But no, I kept my shoes on, my jackets on, my glasses, everything. They just said, there's no walk through. My briefcase didn't have to take laptop out. It was like, really? This is like the old days. Oh, now on the way home I'll get strip searched, of course, because it all evens out sooner or later. Yeah. So, we have one law in groundwater. Okay? Now, what is a law? Okay? Law of gravity. Okay? We've tested it enough times, we've dropped the pencil, it falls down. This is our one law that we have in groundwater. It's called Darcy's law. Okay? Don't panic too much about the giant equation. I throw this up here just so it scares the shit out of you and you have to hire me to do whatever you need done. Okay? Really what it is, it's my permeability number, this K, hydraulic conductivity, the area that I have to move through, and my slope. What's the slope? Is it, it's this height. And that gives me discharge. So now I can calculate how much water is moving through that aquifer or how much water I'm going to get out of the aquifer, which is more important to most of us. Okay? So by using this equation, we can calculate that. But groundwater moves differently in different regions. Around here, it's karst-based, so you're going to have sinkholes and all kinds of disappearing rivers. Arid regions, as we'll see here, it could be wet and dry periods, so water levels do go up and down, and so do the other things. So this all impacts our groundwater resources and changes with the times. This could be due to all kinds of different reasons, obviously. So it brings me to an equation which I think you guys can handle. This is my favorite mathematical equation. It's called the water budget. Okay? It's pretty simple. I have my glass of water. If I add water to my glass of water, what's the water level in my glass do? It goes up. If I drink that water, what's the level of my water glass do? It goes down. This is my kind of math. Okay? But it allows me to actually look at, from a basin standpoint or a watershed standpoint, what's happening with my water resources. Because it's pretty important. Because if I have more going in than I'm taking out, it's just like your bank account, right? That's good. But if I start taking out more than's going in, what's that do to all the water resources in that valley? They all go down. Okay, we're overstretching and using more than we should. So it helps us become more sustainable, which is something we're all going to have to deal with as we move forward. So, some assumptions we make is that we have to usually calculate what recharge is, and we usually look at rainfall. Of course, rainfall is sporadic, right? You can get rainfall in one county and none in the other county, but the watershed or my groundwater basin may cover both counties. So you have to make some assumptions there what the annual recharge might be. What's return flow? Anybody know? Anybody ever heard that term? How many people sit on a septic tank or have a septic tank at their house? Every time you flush the toilet, you're recharging the groundwater. Okay, so we have to make some calculations with that. Okay? And may have to make some assumptions. Other things we have to know is what's the pumping going on in that area, and then surface water and this big evapotranspiration, which is really the plant uptake. Plants steal water from us. Of course, they give us some oxygen, which helps, but they do steal our water. So we basically line up our inputs and our outputs to our bathtub or our glass of water. Our inputs are going to be rain and snow. It's going to be that septic system, what you discharge out the back. It's going to be some streams and springs coming in. But we can also have groundwater coming into our area as well as leaving it. Because our outputs are our usage, our pumping, plants, rivers leaving our area, and then that groundwater leaving the area. Well, it's actually pretty simple to make these calculations. And so what I want to do is give you an example of one we did out in the Mojave Desert, some students of mine. I forgot their names already, so it doesn't matter. Here is our inputs. Here's 3 different people that did this inputs out there, and these are in acre feet. It ranged from about 1,000 to 1,700 acre feet per year into my basin. The outputs were from 4 to 10,000 going out. So what should the water levels in this basin be doing? Going down. Okay? And you see down here all these negative numbers. Well, let's look at safe yield, then I'll show you the hydrograph. Okay, this is straight out of a textbook. Okay, safe yield is the amount of naturally occurring groundwater that can be economically and legally, let me get the lawyers in there, withdrawn from an aquifer on a sustained basis without impairing native quality or environmental damage. Okay? So basically what goes in should equal what's coming out. Here is that same hydrograph I showed you for surface water, but in groundwater. This is water levels taken in a well. Here's 1964. Here's 1999. We're looking at about 80 feet. Okay? Not sustainable. You think sooner or later you're going to run out of water. Okay? But something happened here. Okay? And we're going to talk about that. Okay, so with those hydrographs, which we use in the hydrogeology field all the time. In fact, the USGS does a huge website that they measure hydrographs from waters all over the country, actually all over the world in some cases, and certainly scientists use it. But really, we're trying to get lots of data to see what's happening at those water levels. Well, here's that same hydrograph with some other wells in the same basin. Okay, and they all are showing the same thing. They're all going down. Yeah, there's one anomaly in here where somebody's doing something different, but they're all going down until 1992, I believe it is, or 94. And this is that flat area. So at this point in time, everything was going down until 1994. Then all of a sudden something happened that made it sustainable. Well, what happened is the farmers out in this area were pumping. It's Mojave Desert. They're growing alfalfa. Okay? It's Mojave Desert. What the hell are we doing growing alfalfa out there? They were just pumping out the water. It's easy to get out. It's shallow. Just pump it out, use it. But they weren't taking care of it. So it was going down. So what happened is they had to come in there and force the farmers to start utilizing a certain amount of water based upon the water budgets. Saying, you just can't keep pumping forever at the rates you are. We're going to ramp you down. We're not going to say you can't water. We're just going to say you can't use unlimited amounts of water. We're going to give you some limits. It's called adjudication in California. Okay? So they went in there and said, this is how much water you get. We're going to divide it amongst the people, whatever they did. And ultimately, what happened is at that point in time, everyone agreed, and everybody was able to live nice and happy with one another because everything was flat. They used what they were getting. Now, did that eliminate the farmers? No. They just changed farms. Now they grow almonds and olives, which take a whole hell of a lot less water. And it turns out for some of the farmers there, the successful ones, a lot more, the cash crop was better. So they actually ended up doing a much better job. So ultimately, we can use these hydrographs to look at water level declines or increases in some cases. I got areas where water levels are going up. Okay? Why is that? Because there's less people using it. That can be bad too. In earthquake country, we don't want shallow water tables. Then everything falls down through liquefaction. Okay? We also don't want deep water changes going on the opposite direction either. So it's a balancing act. But it is one that we can handle. Using that simple little equation, we can put our water balance, from a groundwater standpoint, in check. So, groundwater and wells. Well, I love this picture, and there again, I'll share this PowerPoint with anybody who wants it. This is a picture I stole from Johnson Screens, okay? Because I just love it because it shows what the hell it looks like downhole. Remember, we can't see it. Okay? But every time we pump, we end up with drawdown. What's drawdown? Well, if my water table's up here and I start pumping, I'm going to drop the water there. Now, the key with an unconfined aquifer is I'm actually dewatering the aquifer. A confined aquifer, when I pump it, I'm depressurizing it. Okay? So I'm taking water out, but the pressure, remember, is way above maybe potentially land surface. So I'm depressurizing it. I'm not dewatering it. Here, in an unconfined aquifer, I'm actually taking water out of storage. It's coming out of the geology, and this is now part of the vadose zone. And it could be permanent basis, or it may be on a temporary basis. And so what happens is we start pumping, even though our groundwater flow is discharging towards this little creek here, we're basically capturing some of that water which would have gone down here ahead of time and using it for whatever purposes we want. That is not to say this water doesn't come back in here before here and we have a negative zero impact. But it can be a negative impact as well. Okay? And this is something that we're going to have to deal with, is putting water wells next to streams makes a lot of sense. But if we start drying up those streams, somebody's going to notice because they can see the surface water. They don't tend to see the groundwater once again. And certainly we use water for all kinds of fun purposes. And here again, if your septic system sits over here, goes down, over, back up, and you can use it again. What's good about that is what comes out of me can go back in me. Astronauts have shown that for years, right? It's what comes out of you I don't want in me. I don't know what drugs you've been doing. Okay. Which is something we're going to have to worry about. When I talk about 100 million gallons of recycled water every day, one of the things we're worried about is pharmaceuticals. They are small enough to get through the reverse osmosis systems. Now, they're such small quantities that whether or not it does any damage to us, we don't know. You got to remember, the EPA sets their standards on all these on the water quality, but it's based on data from 20 years ago. I mean, they're always 20 years behind. So they're trying to eliminate the risk with who knows what. Oh. And here's just some pictures real quick. Don't worry about the text. Just kind of showing the flow lines here is groundwater flow. I have my recharge area up here, a discharge area down here. It could be a stream or a lake. And you can put your well in there and capture some of it. Or you can do it in a sustainable manner, and there's ways to do that. Lots of calculations go into it. Man's interaction with it. And the picture I want to show you is this one right here. Okay, famous picture, Central Valley of California. What I didn't know until I started teaching was California is responsible for 30% of all the food in the United States as a state. 30% of all the food in the United States comes from California. A lot of it comes from the Central Valley. 1925, the land used to be up there. Now it's down here. That's not due to erosion. That's due to over-pumping the aquifers there and the land subsided. Okay? This is an older photograph. The subsidence there has been nearly 100%, 100 feet. The land has dropped 100 feet. Because they took out all the water, there's nothing to hold the sediment up, it just collapses on itself. And you can actually, from over pumping and stuff in dry areas, you can get these cracks and fissures going over. But something to keep in mind. And this is not just a California thing. We're seeing this in Texas as well as other states. So water quality. Well, when it comes to water quality, keep in mind that groundwater today is the cleanest it's ever going to be in the future. Okay? It's tough to swallow. Why is that? Because everybody in this room, okay, everything we do does something to the water system. Okay? Be it you're taking a pill, you urinate, the wastewater, it's you fertilized your yard. It's the air pollution that gets in the water, that acid rain comes down. It's always going to get worse. So today is the best it's going to be in the future. Okay? That's okay, because the good news is we have engineers whose sole job is to figure out how to clean this shit up. Okay? And their job is to try to provide us with good quality water. Now, does it mean that we can't get good quality water out of the ground in certain areas? Absolutely we can. We still do. But over time, is that going to stay the same? Okay? We have naturally occurring contaminants sitting in the ground. Arsenic and chrome are naturally occurring contaminants. Nitrates are not. Nitrates are man-made. When you find nitrate in your water, that's because somebody put it out there. But yet we have to have the food, right? So we have to have the food. So it's a life cycle we're going to have to deal with. And it can get in the ground all kinds of different ways, straight down, dissolved minerals. Obviously, limestone can get down there quite quickly. Landfills, cars, you name it. Everything we do on the surface impacts our groundwater one way or another. And it's only a matter of time. And if you start looking at China and some foreign countries, we're light years away from them from a water quality standpoint. Why? Because we use groundwater an awful lot. We don't rely on surface water. Okay? The nice thing about the ground is what? It filters shit out. It takes things out. It adds things to it. Why does Orange County in their 100 million gallon recycled system put it back in the ground? Anybody know? Why don't they just give it to us? Because when it comes out of their treatment plant, it's pure H2O. Has nothing in it. Pure H2O, if that's the only source of water you drink, will kill you. It demineralizes you. We need the minerals. We need the geology in order to put the minerals back in the water so when we drink it, it has flavor. Distilled water has no flavor because there's no minerals in it. It has no contaminants either, but that's okay. That just adds flavor. Okay? So we need that geology. We need that groundwater, that water to go into the ground, dissolve some of those minerals, pick them up, because we need those as a human being. Remember, the only thing we are is a little pile of white stuff after you get zapped. Remember the old Star Trek? When they zapped the guy and the only thing left is a little pile of white stuff? All we are is jellyfish with salts. Okay? Well, that's what we need. So we need that water to go back in the ground. So groundwater is always going to be a great source of drinking water. Why does surface water suck so badly for drinking water? Anybody know? Huh? Well, I mean, it's always going to be slightly acidic, but that's not really the problem. What is it? It has low mineral count and it fluctuates. Okay, it's at the surface, so flow-wise it fluctuates a lot more than groundwater. Groundwater is pretty steady. Other thing is, it doesn't take a whole lot to contaminate surface water. It actually takes quite a bit to contaminate groundwater. Okay, so groundwater is always going to be a safer source of water, ultimately. Okay. Certainly, we're going to, land farming and all that good stuff. Landfills are always easy to point out. Factories are always, bad things, but we all like our, iPhones and everything else. I point out there's a 7-mile plume of TCE under City of Phoenix. Why? Because somehow City of Phoenix wants to make a lot of transistors. Okay? But every transistor requires 170 to 180 gallons of pure water. It's in Phoenix, Arizona. Why wouldn't we put this in the tropics somewhere where they actually have lots of water? 180 gallons per transistor. Now, how many transistors in your cell phone? Yeah, every cell phone. I mean, you add it up. I mean, we're talking thousands of gallons of water just to make one phone. And it's in Phoenix, Arizona. Who knows? Some tools we use to investigate things. We're starting to use remote sensing a lot more. I can't wait to get my own drone. So I can drop bombs on ex-girlfriends or ex-wives, whatever it is. But nonetheless, I want a drone. That's just cool. Okay? And we're going to get our Amazon's going to deliver all our packages by drones now. You order it in 30 minutes. The little drone flies at your front doorstep, drops your book, and off it goes. Okay? So it's going to be cool, and it's going to be some fun things, but we use geophysics. Here's some geophysics out in the beach in Lake Michigan. We're looking for some clay units for discharge into Lake Michigan. A lot of computer modeling is taking place now, which is allowing us to do some things. There again, the problem with it is it's only have crappy data. You can make a pretty picture, but if it's crappy data, it doesn't mean much. But there's going to be a lot of advancements here over the next decade. It's going to be kind of fun. And like I said, the drone thing is something I'm excited about. In fact, I have my own blimp, by the way, and I've had one for 20 years. That's how I've been taking my area photographs. So I actually own my own blimp. How many people do you know that? How many people in here own a blimp? See? Special. So anyway, hopefully you learned something about basic definitions and some water quality and some other things. We went through some things come up fast, but nonetheless, I want to thank everybody and thank Cal State Fullerton and NGWA for allowing me to be here. And I appreciate everyone's time and thoughts. Any questions besides the code? Yeah. Any questions? Yeah, go ahead.
The Oklahoma is being depleted at a rate that is also causing it to collapse.
Absolutely.
And that will never be replaced.
We can take steps to start replenishing parts of it, but overall, we're probably not going to gain it back unless climate changes again, in which it gets rainy, which could happen. I mean, it was an old sea to begin with, so maybe it comes back to being that. Maybe you can get some oceanside property there. But certainly there's things we can artificially do to recharge. Some of the things people are doing a lot more. What Orange County does was a gamble. We spent $4 to $5 billion to set up this system. And it had to go through all the EPA and everything else, and it was just amazing. But then now they've gotten to the point where they've proven, beyond any reasonable doubt, and other countries are modeling this too. Singapore, their whole system is designed after Orange County, Saudi Arabia, everyone else. And that is taking the water that we use for whatever purpose. I mean, I talk about wastewater and toilet water, but it's 48 hours from the time you flush your toilet to that water drop being back in the ground. Okay, 48 hours. So that's going to happen more, and if we do that, ultimately during the wet years, in order to become sustainable, the wet years will fill things up if you can become sustainable in the short cycle. From farming standpoint, we have a lot of return flow because we're getting better about it, because that's one thing, when we farm, we always overwater, because more water is going to make it greener. Well, it isn't always the case. So the farmers have done a better job now of managing the soil moisture, so they water when the plant really needs it. So that's helping sustain that a little bit, and that should help bring some stuff back. But ultimately, it'd be as more of this urban water cycle than wait for the wet years to bring back things to a bigger, fuller situation. So, yeah. Other questions? None? Anybody asleep yet? Yeah.
I don't understand. Did we take nitrogen and oxygen and make water?
Yeah. Every time you sweat. Like me right now. I got lots of H2O underneath my armpits. Well, the problem is you can't, it's economically. It just comes down to economics, like desalination. We live in California. We got the world's largest ocean sitting right there, the Pacific Ocean. Why won't we just take the water from there, get rid of the salt, and use that for drinking water? And we are. The problem is from a cost standpoint, it's about, in 2000, it was about $2,000 an acre foot to treat desalinated water. We could buy water from anywhere else in the country for about $1,000 or less. We stole from the Colorado, we steal from San Francisco. We can buy Lake Michigan for cheaper than that. Okay, now Michigan's passed a law that we can't. Specifically California, can't steal the water. By the way, why they had to pass a law for that, who knows? But they did. Okay, but now the desalination is about $1,000. What Orange County is doing is about $900 an acre foot for its whole system. So we're still cheaper than that. Sooner or later, desalination price-wise will get down where it makes sense. But from an energy standpoint is where it really costs. And so just like making H2O, yeah, we can make it. We can have hydrogen cars. Why don't we? Because of cost. And it's just over time. Worse as we move forward. That means there's going to have to be a cost to water. Water is free. You only pay for delivery. Okay, now you pay for some treatment of the water, but you're actually not buying the water. You're buying the delivery of the water. And of course, my wife's one of those people. We live in the city, and she complains about the taste of it all the time. I taste the chlorine. Why do we put chlorine in water? Well, it keeps all the bacteria from killing you. It kills all the bacteria. Not in their pipes, not the city's pipes. Their pipes are fine. It's your house. Where's the worst spot for bacteria for water? At your faucet. What's the worst kind of water you can ever get? Take a 5-gallon jug down to your local grocery store, and that big thing out in front, it's attached to a garden hose, by the way. There's tons of bacteria there. And yet people are still sitting there buying their 5-gallon bottle of water because it has to be good. It came from the grocery store. We pay as much for water as beer. At least beer is distilled, and I get happy over it. I need T-shirts. Drink beer, not water.
So back to Orange County.
Yep.
And the reclamation process. How come more cities aren't doing that? Is that the cost effectiveness that you mentioned?
Well, and it also depends on where you're at. In Orange County, we have 4 million people, and we're a desert. We only get 16 inches of rain a year. So it made sense for us to be more of that system. If you're in Minnesota, up until this point in time, they had 10,000 lakes. There's plenty of water. So they don't need to do it. Atlanta, Georgia, the river that they ran the Olympics, the kayaking, I guess, is dry. There's no water in that river anymore. They could not run the Olympics today in Atlanta, Georgia. And it's because they dropped all the water, they stole all the water from the river and had fights with the other states and other things. There's a lot more to it. But they're looking at recycling stuff. It's why Coca-Cola is doing a big push on trying to do water recycling. Recycle the plastic bottles. I mean, the same thing holds true for water as for trash and everything else. I hate to use the word sustainable because 99% of the public doesn't even know what the hell it means. It's a cool word. It's sexy. I can write sustainability on any grant and get it. Doesn't mean it has anything to do with sustainable, but when we use 100 gallons of water and we don't have to buy it from anyone else, we are now sustainable. It's a cost to that, but we are not having to borrow water from anyone else. So, other questions? Someone else had one?